If the universe had a birth certificate, it wouldn't be written in ink on paper. It would be written in a cold, invisible glow. A glow older than the stars, older than the first atoms, whispering from every possible direction in the night sky all at once. And tonight, right here in this dim control room, you and I are going to interrogate that glow like forensic detectives. Why? Because there is a massive scandal hiding in the night sky. The universe looks suspiciously, uncomfortably coordinated. It is far too smooth to be an accident. It is far too mathematically balanced to be casual. So, what actually happened in the very first fraction of a single second? Did the entire universe grow too fast to be real? Look at the monitors in front of us. They are painting the invisible sky in false color. You are seeing temperature maps, polarization vectors, and statistical uncertainty bars that look like tiny, fragile fence posts guarding our confidence. The room smells faintly of warm electronics and ozone. Outside these walls, the night is perfectly quiet. But inside this data, the cosmos is screaming. You just need to know how to listen. Here is the fundamental, deeply human question that drags cosmologists into this mystery. It is the question that absolutely refuses to leave you alone once it gets lodged inside your mind. How did the universe become a place where anything could form at all, without someone or something fine-tuning every single detail by hand? Because when you and I walk outside and look upward, we do not just see empty, dead space. We see a massive, unfolding story with strict rules. And those rules are weirdly hospitable. I don't mean hospitable in a warm, sentimental way. Space makes no promises and offers zero mercy. But it is hospitable in the strict physical sense that it permits complexity. It allows atoms to bond. It allows chemistry to ignite. It allows planets to coalesce, biology to evolve, and whatever it is inside your brain right now that can sit still long enough to wonder why any of this exists. Now let me show you the raw evidence that makes the greatest physicists in the world sit up straighter in their chairs. Look closely at the main screen. This is the cosmic microwave background. We call it the CMB. It is the absolute oldest light we can ever see. Think of it as a fossilized photograph, taken when the universe was just a baby, still trying to decide what it was going to become. At first glance, this map of the CMB looks almost exactly the same in every single direction. It is nearly uniform, nearly featureless. It looks like a perfectly, flawlessly painted wall. But here is the catch. It is not perfectly uniform. If you zoom in, it has freckles. Tiny, microscopic differences in temperature, varying by only about 1 part in 100,000. These variations are minuscule. They are incredibly easy to ignore. And yet, those tiny freckles are the most important thing you will ever look at. Because those tiny temperature variations are the earliest known seeds of all physical structure. Without them, there are no galaxies. There are no superclusters. There is no vast cosmic web. And eventually, there are no heavy elements to forge the calcium in your bones or the iron in your blood. So, here is our pact. Just you and me, right now, in this room. We are not going to treat cosmic inflation like some sort of sci-fi vibe. We are not going to treat it like a comforting myth that we repeat just because it sounds grand and poetic. Inflation is a hard, scientific claim, and it carries massive consequences. If it actually happened, it absolutely must have left a physical signature. It must have left its fingerprints smeared across the sky. This is the science audit. Together, we are going to step backward into the very first fraction of a second of existence. We are going to reconstruct exactly what must have occurred. And then, we are going to come back to the present day holding a strict checklist of tests. Tests that nature has already graded, because the universe keeps meticulous records, whether we bother to look at them or not. So, come closer. Imagine the lights in this control room dimming even further. We are about to travel back to a time when the words, room, and outside, do not even mean what they mean today. We are going back to a time before atoms existed. Before light could even move freely. We are dropping into a universe so unimaginably hot, and so intensely dense, that photons, the fundamental particles of light, cannot travel more than a microscopic hair's breadth before they violently crash into something charged and get scattered in a new direction. We are plunging straight into the early cosmos. Do not picture an empty black void. It is not empty. It is a blinding, seething, roaring plasma. It is a soup of free-floating electrons and raw atomic nuclei, with light permanently trapped inside it, bouncing around like car headlights lost in a dense, impenetrable fog. If you could somehow survive being there, if the concept of there even applies, you would not see any stars. You would not see space as we know it. You would be trapped inside a glowing, omnidirectional storm where light itself is a prisoner. For hundreds of thousands of years, the universe exists in this suffocating state. But space is expanding. And as it expands, the universe begins to cool. But it doesn't cool gently, like a cup of tea sitting on a wooden table. It cools more like a blast furnace being systematically dialed down by the stretching fabric of reality itself. Eventually, roughly 380,000 years after the Big Bang, the temperature hits a critical, magical threshold. About 3,000 Kelvin. Suddenly, the chaotic energy drops just enough. The free-roaming electrons slow down. They get captured. They finally settle into stable, quiet orbits around the atomic nuclei. The first true atoms of hydrogen and helium are born. The charged particles are locked away. And in a cosmic instant, the dense, blinding fog totally clears. Suddenly, for the very first time in the history of reality, light is completely free to fly. Physicists call that spectacular moment the surface of last scattering. It is not a physical surface, like a brick wall. It is more like the last, outer layer of a fog bank that you can finally see through. It is the absolute earliest epoch from which photons can travel to our telescopes unimpeded. The cosmic microwave background is that exact ancient light. It has been flying through space for 13.8 billion years. But as it flew, the universe kept expanding. Space kept stretching. And as space stretched, it stretched those light waves along with it, lengthening them, pulling them out of the visible spectrum, all the way down into microwaves. Today, that blinding primordial flash has cooled into a faint, invisible afterglow, hovering just 2.7 degrees above absolute zero. And this is exactly where our instruments, our machines, and our brilliant human paranoia come into play. We do not just look at the CMB like it is a pretty piece of abstract art. We measure it. We audit it. We dissect it like forensic accountants measuring an impossibly complex financial ledger. We measure the temperature anisotropies, those tiny hot and cold variations across the sky. We measure the intricate polarization patterns, the subtle, directional alignments in the light's electric field, much like the grain in a piece of carved wood revealing exactly how it was shaped. We measure the deepest statistical properties, how the magnitude of these fluctuations varies depending on the scale you look at. When cosmologists use the phrase, nearly scale invariant power spectrum, I want you to picture this metaphor. Imagine the infant universe is playing a massive, complex musical chord, not just a single, lonely note. Nearly scale invariant means that the volume of this cosmic chord is almost exactly the same across all the different octaves. The patterns of different sizes, the huge patches and the tiny patches, all have a nearly consistent, harmonious strength. And let me be clear, there is incredibly stable ground under our feet here. The standard Big Bang picture is not just one lonely, fragile claim. It is a tightly braided rope of independent, verifiable evidence. Big Bang nucleosynthesis mathematically predicts the exact abundance of the lightest elements in the universe: hydrogen, helium, and a tiny dash of lithium. And when we look out into the oldest gas clouds, the universe perfectly matches those predictions with eerie, chilling fidelity. The Hubble-Lemaitre expansion proves that space itself is physically stretching, dragging galaxies away from us, leaving a cosmic history perfectly encoded in the redshift of their light. The CMB itself possesses an almost mathematically perfect blackbody spectrum, meaning it conclusively looks like radiation that emerged from a universally hot, dense system that cooled down smoothly. It is quite literally one of the cleanest, most irrefutable signals ever discovered in all of empirical science. So, if this standard story is so incredibly successful, why is the atmosphere in our control rooms so tense? Why do the world's smartest cosmologists keep this particular case file sitting open on their literal and proverbial desks for decades? Because the exact same CMB that loudly confirms the Big Bang also reveals massive, glaring cracks in the foundation. There are 3 famous cracks. And they are famous for a very good reason. They are not little technical hiccups. They are not rounding errors. They are deep, fundamental, conceptual nightmares that force you to question whether our basic story of reality is missing a massive, crucial chapter. Let's audit the first crack, the horizon problem. Look back at the CMB map. Take a point on the far left side of the sky, and another point on the exact opposite far right side of the sky. They are billions of light years apart. Yet they have the exact same temperature, down to the 5th decimal place. But in the standard, vanilla Big Bang expansion model, those two regions of space were absolutely never in physical contact with each other. Even in the very beginning, they were expanding away from each other so fast that light, or any form of information or heat transfer, could not possibly travel between them to equalize their temperatures. Think about how insane this is. It is exactly as if you walked into a massive football stadium where two totally separate crowds, who have been locked behind impenetrable soundproof walls since the moment they were born, are suddenly chanting the exact same complex song, in perfectly synchronized rhythm, down to the very millisecond. How in the world did they agree on the rhythm if they could never, ever communicate? That is the horizon problem. Now, the second crack, the flatness problem. When cosmologists say the universe is flat, they do not mean it looks like a two-dimensional sheet of paper. They mean it geometrically. They mean that parallel lines will always stay parallel, exactly the way you learned in high school geometry. They mean that if you draw a triangle across billions of light years of space, the interior angles will add up to exactly 180 degrees. No warping. No bending. Every observation we make shows the universe is astonishingly, perfectly close to flat. But here is the nightmare for the standard model. In the math of general relativity, flatness is incredibly unstable. If the early universe had been even slightly curved, even by one tiny fraction of a percent, that curvature would have rapidly grown and amplified over cosmic time, becoming violently obvious today. The universe would have either rapidly collapsed back in on itself, or blown apart so fast that no stars could ever form. The fact that it is still perfectly flat today means the universe at the moment of the Big Bang had to start out tuned to an absurd, incomprehensible level of precision. I am talking about 1 part in 10 to the power of 60. That is like balancing a microscopic pencil on its infinitely sharp tip during a massive magnitude 9 earthquake, walking away for 14 billion years, and coming back to find it is still perfectly standing. It defies all logic. And the third crack, the monopole problem. When you run the math of high-energy particle physics, specifically grand unified theories, they predict that the extreme heat of the early universe should have forged massive, heavy relics called magnetic monopoles. These are theoretical particles that carry only a north magnetic pole, or only a south magnetic pole. If the standard Big Bang story is totally complete, the universe should be absolutely swarming with these heavy relics today. They should be everywhere. But we look out, and we see zero. None. The universe looks completely, suspiciously clean. It looks like the crime scene was meticulously swept. At this specific point, it is incredibly tempting to do exactly what human beings always do when the physical evidence gets incredibly uncomfortable. It is tempting to just shrug our shoulders and say, well, maybe the universe just miraculously started that way. Maybe it was just born perfectly balanced. But listen to me carefully, that is not an explanation. That is intellectual surrender dressed up as scientific humility. The only honest response is to look at the data, admit that we are deeply missing something, and then go hunting for the real mechanism. Now we step right up to the very edge of human understanding. We arrive at the exact moment in this story where the chalkboard equations stop feeling like academic homework and start feeling like literal prophecy. There is a radical hypothesis that was proposed to solve all three of these impossible problems in one single, elegant stroke. It does not just put a band-aid on the Big Bang, it completely rewrites the entire opening scene of reality. It is called cosmic inflation. But inflation is a heavily loaded word. When you hear it, your brain immediately pictures an explosion. You picture hot stuff flying rapidly outward into a pre-existing, empty, dark room. I need you to completely delete that image from your mind right now. That image will entirely betray your understanding. Let's translate inflation into a physical concept you can actually feel. Imagine you are standing on a gigantic, infinitely stretching sheet of black rubber. And printed onto this rubber sheet is a white grid, little intersecting lines acting like cosmic ruler marks. During inflation, you are not watching objects physically race across the surface of the sheet. You are watching the grid itself violently stretch. The actual, physical distances between the ruler marks are growing. If you place two tiny ants on this sheet, and they are standing perfectly still relative to their little local square of rubber, the absolute distance between them will still rapidly increase, simply because the floor beneath them is swelling. Local physics stays entirely local. The atoms, the forces, the light beams, they all still behave totally normally inside their tiny, local neighborhoods. But the overall background geometry of reality is expanding at an absolutely terrifying rate. Cosmic inflation makes a deeply specific, staggering claim. It says that for a profoundly brief moment, an absurdly, impossibly brief fraction of a second, somewhere around 10 to the minus 36 seconds after the beginning, the actual fabric of space expanded acceleratedly. It wasn't just expanding at a steady pace. The expansion itself was speeding up, compounding on itself exponentially. The universe didn't merely grow. It underwent a violent, exponential growth spurt so incredibly severe that it took a patch of space smaller than a single proton and blew it up to the size of a grapefruit, or perhaps even larger, faster than the speed of light. And right there, that violent, faster-than-light stretching of the grid, is exactly how you get the coordination we see in the sky today. Everything we can possibly observe in our visible universe today originated from a microscopic, localized patch that truly was an intimate physical contact. That tiny patch had plenty of time to exchange heat. It had plenty of time to thermalize. It had plenty of time to agree on a perfectly uniform temperature and settle into total equilibrium, long before the violent hammer of inflation dropped and violently stretched that tiny patch out to cosmic, unimaginable proportions. It solves the horizon problem instantly. The crowds in the stadium are singing the same song because, before the stadium was built, they were all sitting together in the exact same tiny room, sharing the exact same sheet music. Inflation makes a massive promise. If it truly happened, the universe absolutely must look flat to us today. Why? Because any initial curvature, any warping or bumps in the early fabric of spacetime, gets violently ironed out, exactly like pulling a wrinkled bedsheet extremely tight from all four corners. It makes the monopole problem instantly vanish into irrelevance by taking those heavy relics and diluting their density to practically zero. It is like taking a tiny handful of sand, representing the monopoles, and violently scattering it across an ever-expanding, infinite desert. You would never, ever find one. But now, here comes the ultimate pivot. This is the exact moment where the story stops being strictly about gravity and geometry, and becomes a mind-bending story about the microscopic quantum world violently leaking into the macroscopic cosmic world. Because for this universe to exist as it does, inflation desperately needs seeds. It needs a physical mechanism to create those tiny temperature freckles in the CMB, without God carefully painting them on by hand. And this is where nature pulls off something that feels exactly like a magic trick, right up until you learn the underlying rules. In the realm of quantum mechanics, absolute emptiness does not exist. A total vacuum is not a silent, dead void. It is completely alive. It is far more like a chaotic, restless ocean. At the subatomic level, underlying quantum fields are constantly jittering. Energy is perpetually fluctuating. So-called virtual particles are spontaneously popping into existence, borrowing energy from the vacuum, and then instantly annihilating each other and vanishing back into the void. They exist only in fleeting, microscopic whispers allowed by Heisenberg's uncertainty principle. It is exactly like the chaotic, bubbling foam briefly popping up on the crest of an ocean wave, only to violently collapse back into the water before you even have time to count it. Under totally normal circumstances, these tiny quantum fluctuations are strictly microscopic and strictly transient. They stay incredibly small. They wash themselves out. They are mathematically irrelevant to the large-scale universe. But during the violent epoch of inflation, the rules fundamentally break. Space is suddenly stretching so unbelievably rapidly that it can literally grab those microscopic, transient quantum ripples and violently rip them apart. It pulls them far beyond the microscopic scale, freezing them in place before they have the chance to collapse and smooth themselves away. Imagine taking the delicate, tiny, rippling patterns on the surface of a liquid pond, and suddenly, magically flash freezing the entire pond into solid ice, while simultaneously stretching that ice out to the size of a continent. You have just taken a microscopic, temporary quantum pattern and permanently locked it in as a massive, macroscopic feature of reality. This is the ultimate eureka moment of modern cosmology. Galaxies are not just objects in space. Galaxies are literally built from amplified quantum uncertainty. The grand, sweeping architecture of our universe, the massive cosmic web spanning hundreds of millions of light years, the great walls of galaxies, the massive voids of nothingness, can all be traced directly back to subatomic quantum fluctuations that began smaller than a single atom. I really want you to just sit with that for a moment. Let it sink in. The universe's absolutely largest physical structures are nothing more than the violently grown-up versions of the universe's absolutely tiniest subatomic indecisions. But remember the pact we made at the start of this video. As scientific auditors, we do not just sit back and marvel at a beautiful story. We demand receipts. We look at this beautiful mathematical framework and we ask, what does inflation actually predict that we can measure today? What physical data could we pull from the sky? What would count as a definitive, unarguable signature, rather than just a convenient bedtime story? Well, inflation violently predicts that the universe should be nearly flat. And our satellites confirm it is flat to within an incredibly tight margin of error. It predicts correlations in the CMB on massive angular scales that, in the standard, non-inflationary Big Bang model, simply should not be able to talk to each other. We call these superhorizon correlations, and we see them clearly in the data. It mathematically predicts a specific spectrum of primordial density fluctuations that is nearly, but critically not perfectly, scale invariant. It predicts that exact cosmic chord across all the octaves, with a very slight, specific tilt in the power spectrum. And when the Planck satellite mapped the sky, it found exactly that tilt. Furthermore, it predicts that these tiny density fluctuations should be incredibly close to Gaussian. What does that mean? It means if you plot their statistical distribution on a graph, they should resemble a highly familiar, highly predictable bell curve. This is exactly the kind of natural distribution you get when millions of tiny, independent, random quantum events add up together over time. Now, it might not be perfectly Gaussian. Small, incredibly subtle deviations, which physicists call non-Gaussianity, can technically exist. And hunting for that exact non-Gaussianity is one of the most vital ways cosmologists are trying to discriminate between totally different, competing models of inflation today. But inflation may predict something even more profoundly intoxicating. Something that could win Nobel Prizes and cement our understanding of reality forever. It predicts a faint, lingering background of primordial gravitational waves. I am not talking about the violent gravitational waves caused by two massive black holes crashing into each other. Those are just localized cosmic fireworks happening very late in the universe's history. I am talking about the faint, pervasive, omnidirectional tremor of space-time itself, generated during the violent tearing of the inflationary epoch. It would be a literal, physical whisper from an era of energies so incomprehensibly high that no particle accelerator built by humans will ever be able to reach them. If that primordial tremor truly exists at a level we can detect, it would imprint a highly specific, undeniable pattern into the polarization of the cosmic microwave background. We call this pattern B-modes. Let me translate the jargon for you. Polarization is essentially the direction that a wave of light is wiggling as it travels through space. In the hot plasma of the CMB, normal, standard density variations produce a polarization pattern called E-modes. These E-modes look very clean. They look like parallel lines, or radial spokes on a bicycle wheel. But passing gravitational waves do something totally different. They physically stretch and squeeze the fabric of space, and this twisting motion forces the light's polarization into a complex, curly, swirl-like pattern. That unmistakable swirl is the B-mode signature. Finding a primordial B-mode swirl in the sky is exactly like dusting a crime scene and finding a perfect, glowing fingerprint that only one specific suspect could have plausibly left behind. But as auditors, we have to be incredibly, ruthlessly careful. The universe is unbelievably messy. It loves to lie to us. Our own Milky Way galaxy is absolutely filled with swirling clouds of interstellar dust. And guess what? When magnetic fields align that galactic dust, it emits microwaves that can perfectly mimic the exact swirling B-mode pattern we are desperately looking for. We learned this the hard way. Human instruments have systematics, and bad systematics can easily mimic absolute certainty. In this elite line of forensic cosmology, the absolute most dangerous sentence you can ever utter is, "Well, it looks like it." So, our scientific audit must explicitly include what the theory of inflation does not tell us. Inflation, as it is usually stated in textbooks, is essentially a broad framework. It is a family name, not a specific individual. It typically involves a theoretical scalar field called the inflaton. This is the hypothetical energy field whose rapid roll-down and energy slope drives the accelerated expansion. But here is the brutal, honest truth. We have absolutely no idea what the inflaton field actually is. Is it a brand new, undiscovered fundamental particle? Is it some exotic configuration of the fields we already know, like the Higgs boson? Or is it just a convenient mathematical placeholder for a much deeper, much stranger physics that we have not even met yet? We simply don't know. We don't know the exact shape of its potential, the mathematical energy landscape that strictly governs exactly how the inflation speeds up and slows down. We don't fully understand the initial conditions, what specific cosmic spark forces inflation to kick in the first place? And we deeply struggle to understand exactly how it cleanly ends. How does the universe achieve what physicists call a graceful exit? How does the energy of the rapidly expanding vacuum suddenly dump itself into the creation of particles, a process called reheating, which basically ignites the hot plasma of the standard Big Bang story? These are massive, gaping holes in the file. And then, we must address the most controversial consequence of all, the multiverse concern. The mathematics of some of the most robust versions of inflation suggest a terrifying idea. They suggest that once the inflationary expansion starts, it can never entirely stop everywhere at once. It can keep happening infinitely in isolated, separated pockets. This is called eternal inflation. It creates a vast, fractal-like landscape, a bubbling multiverse of different pocket universes, each potentially possessing completely different laws of physics. It is an undeniably profound, beautiful idea. But it is also an incredibly dangerous one for science, because if a theory predicts literally everything is possible somewhere in the multiverse, then it risks predicting absolutely nothing specific that we can test here in our own universe. In the science audit, we do not hand out medals for ideas just because they are grand or beautiful. We strictly reward ideas for making hard, falsifiable contact with raw data. So, as good detectives, we must ask, what if inflation simply isn't the only way to solve these cracks in the Big Bang? There are entirely alternative proposals out there. There are bouncing cosmologies, where a previous universe slowly contracted down into a dense, hot state, and then violently rebounded into an expansion, entirely avoiding the impossible singularity of a definitive beginning. There are radical scenarios where the absolute speed of light itself was much, much faster in the early universe, which would have allowed those distant, disconnected regions of the sky to easily communicate and equalize their temperatures without needing any hyperexpansion. There is string gas cosmology. Each of these brilliant alternatives comes with its own unique set of predicted signatures. They predict different patterns of statistical non-Gaussianity. They predict vastly different relationships between the density fluctuations and the gravitational waves. Some predict zero primordial gravitational waves at all. This is not a high school popularity contest. It is forensic science at the ultimate limit of reality. Nature already picked exactly one real history. Our only job as a species is to build the tools necessary to read the crime scene correctly. So now, bring your attention back to this dim control room. Because this is the exact moment where the abstract mathematical story becomes intensely physical again. This is where brilliant human beings build massive, impossibly complex machines out of glass, silicon, and supercooled metals to read the universe's receipts. The European Space Agency's Planck satellite already gave us a definitive, legacy map of the CMB with absolutely exquisite precision. It dramatically tightened the constraints on the power spectrum and ruthlessly confirmed that the quantum fluctuations are remarkably close to perfectly scale invariant, and highly Gaussian. Ground-based telescopes, sitting in the high, dry deserts of the Atacama, like the Atacama Cosmology Telescope, ACT, and at the literal bottom of the world, like the South Pole Telescope, SPT, stare relentlessly at the sky. They use different strengths, higher angular resolution, multiple frequency bands, to painstakingly separate the true primordial signal from the confusing foreground dust of our own galaxy. And then there are the dedicated, hyper-focused polarization hunters. Instruments like Bicep and the Keck array. They do not look at the whole sky. They stare relentlessly at carefully chosen, incredibly clean, incredibly dark patches of the southern sky, desperately trying to detect that faint B-mode swirl that would instantly rewrite physics textbooks around the globe. But the Audit does not stop there. Future, next-generation satellites are already being planned with exponentially more sensitivity, because the target signal is frustratingly faint, and the universe absolutely refuses to hand over its deepest secrets cheaply. Meanwhile, massive large-scale structure surveys are actively mapping exactly how matter clumps together across vast spans of cosmic time. Instruments like DESI are measuring the exact redshift of millions of galaxies, creating a 3D map of the universe's expansion history. The Euclid Space Telescope is mapping cosmic geometry and the invisible dark matter web via gravitational lensing. The upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time is poised to deliver a literal, high-definition time-lapse video of the visible universe, revealing incredibly subtle patterns in exactly how cosmic structures grow and evolve over billions of years. Let me be clear, these are not separate, isolated science projects. They are vastly different forensic angles looking at the exact same ancient crime scene. And sitting right on the bleeding edge of the horizon is 21-centimeter cosmology. This is the ambitious, incredibly difficult attempt to use the faint radio signal emitted by neutral hydrogen gas to map the universe's dark ages, the long, cold epoch long before the very first stars even ignited. It is exactly like discovering a completely untouched, deeply buried layer in an archaeological dig, one that is significantly closer to the explosive moment we actually care about. The scientific promise of 21 centimeters cosmology is absolutely enormous. The technical, engineering challenge is utterly brutal. But if humanity can make it work, it could give us a true, high-resolution, three-dimensional view of the primordial quantum fluctuations, rather than just the two-dimensional snapshot we get from the CMB. So, here is the ultimate suspense that keeps this entire field of physics awake at night. The hunt for primordial gravitational waves. If we eventually detect a clean B-mode polarization signal, and we prove it has the right frequency dependence to rule out dust, the right angular power spectrum, and it passes every single ruthless cross-check we can throw at it, then we have done it. We are literally hearing the heartbeat of inflation. We are directly, physically probing new physics at energy scales that dwarf anything humanity could ever build on Earth. But what if we don't detect them? What if the screens stay blank? Does that mean inflation is automatically dead? No. Many theoretical models of inflation naturally predict that the gravitational waves would be far too faint for our current instruments to ever see. But here is the critical part. Entire massive classes of inflation models would be permanently ruled out. The space of mathematically plausible theories would radically shrink. In the world of the science audit, non-detection is not a failure. Non-detection is pure, hard information. It is the universe firmly answering us, saying, "No, not that way." Now I want you to slow down with me for a second. Because this is the exact moment where the massive, cold, abstract cosmos becomes deeply, unavoidably intimate. If the theory of cosmic inflation is fundamentally right, then the universe we are currently living inside of is, in a very literal, physical sense, the highly amplified, macroscopic shadow of quantum uncertainty. The totally random, unpredictable jittering of subatomic fields, occurring in the tiniest fractions of a second at the dawn of time, became the permanent, physical blueprint for absolutely everything that followed. Your physical body is not separate from that story. The carbon currently structuring your cells was forged inside the crushing cores of dying stars, yes. But those stars only formed because hydrogen gas clumped together. That gas only clumped together because there were tiny, microscopic overdensities in the early plasma. And those overdensities trace perfectly back to the tiny temperature freckles in the CMB. And those freckles trace perfectly back to subatomic quantum fluctuations that were violently stretched across the infinite sky by inflation. Which ultimately means there is a direct, unbroken, physical, causal line extending from the chaotic quantum foam of the infant universe, all the way to the absolute, staggering fact that you currently possess a functioning nervous system capable of feeling awe. It is incredibly easy to feel overwhelmingly small when you hear a fact like that. But you can also choose to feel deeply, profoundly included. Because the universe is not just some cold, empty container that you happen to be stuck inside. It is literally something you are made of. You are the universe looking back at itself. And the physical evidence of its earliest moments is still constantly arriving here at Earth, photon by photon, washing over our antennas like heavily delayed mail delivered from the absolute beginning of time. There is also a deep, vital philosophical lesson buried in this data that I think science sometimes forgets to say out loud to the public. The universe might be comprehensible to us not because it is simple, but simply because it left a readable record. Reality keeps receipts. The cosmic microwave background is a receipt. The exact measured abundance of helium in space is a receipt. The sprawling, web-like distribution of galaxies is a receipt. The trick of cosmology isn't to invent the flashiest, coolest sounding mathematical story. The trick is to match all the physical receipts perfectly, without ever cooking the books. And we have to keep our intellectual honesty completely intact as we move forward. It is entirely possible that over the next decade, we firmly confirm inflation's broad, sweeping signatures, the extreme flatness, the near-scale invariance, the Gaussian statistics, without ever actually identifying the exact subatomic mechanism that caused it. That would be a massive, historic partial victory. We would know the exact kind of dynamic event that happened, even if the true identity of the physical actor remains hidden in the shadows. It is also entirely possible that new data falsifies all of our most popular inflation models, and the universe forces us to confront an entirely deeper mystery, one we don't even have a name for yet. But I want you to notice exactly what that means. Either way, we win. We are not trapped in ignorance. We are not doomed to superstition or blind guessing. We are actively doing something unbelievably, profoundly rare in the long history of human thinking. We are actively testing complex mathematical claims about the very first fraction of a single second of physical existence, using incredibly precise measurements made today by highly evolved primates living on a tiny, rocky planet, holding up sensors built from melted sand and forged metal, perfectly cooled and calibrated, staring out into the dark sky. So let's end exactly where we began, right here in this quiet control room, with the sky fully rendered as hard data on the screens in front of us. Look closely at the map one last time. Every single pixel on that screen represents a physical direction in space. Every direction is a continuous, roaring stream of ancient photons. And every single photon is an eyewitness to the birth of reality. They are not witnesses with biased opinions. They are just pure physical witnesses, carrying a specific trajectory, a specific frequency, a specific polarization state, and a permanent timestamp burned into their own frame of reference. But when you put them all together, they stand up and they testify. Here is the ultimate synthesis of the audit, stated as cleanly as I can possibly say it. The standard Big Bang model explains the universe's broad, sweeping evolution with absolute, extraordinary success. But it leaves behind deep, maddening puzzles, impossible coordination across the sky, extreme, unbelievable flatness, and glaringly missing relics. Cosmic inflation is the proposed missing chapter. It is a brief, violent era of accelerated, exponential expansion that makes all of those impossible puzzles feel completely natural, and that miraculously turns chaotic quantum fluctuations into the permanent seeds of cosmic structure. It is not just a single, fragile theory. It is a robust framework that absolutely must be audited by its measurable consequences, especially the highly detailed statistics of the CMB, the vast structure of the cosmic web, and perhaps one day, the definitive discovery of a primordial gravitational wave signature hidden in the polarization of light. Now, before we close the file, I want to give you a specific thought experiment to carry away with you into your own life, because I promise you, this is not just about the cosmos. Imagine for a second that somewhere deep inside your own earliest, fuzzy childhood memories, your very first feeling of fear, your very first moment of joy, there were faint, underlying patterns that you didn't consciously choose. Patterns laid down long before you even possessed language, long before you had any real agency. Those patterns do not absolutely dictate exactly who you will become, but they heavily nudge what is mathematically likely. Cosmic inflation, if it is fundamentally true, is exactly like that for the entire universe. The earliest, chaotic quantum ripples did not strictly determine every single tiny detail of reality, but they permanently shaped the probabilities of absolutely everything that followed. And that realization rips open the next great, terrifying question, the exact question that makes the air in this control room feel thick and electric. If we ultimately confirm that inflation definitely happened, what, exactly, was the physical thing that inflated? Was it a real, tangible energy field? Was it some bizarre, multidimensional shadow of quantum gravity? Was it just a crude mathematical placeholder for a much deeper, more beautiful theory of everything? And if inflation didn't actually happen, if the physical receipts ultimately don't add up, then what in the world came before the Big Bang as we understand it? Before you leave this room, I need you to do something that massively helps this channel grow and, far more importantly, actively helps cement your own understanding of the physics we just covered. Tell me down in the comments exactly what piece of evidence would finally convince you. Pick just one clear thing. Would it be the undeniable discovery of B-mode polarization? Would it be a specific, measurable kind of non-Gaussianity? Would it be shocking new evidence of spatial curvature? Or do you think it would take an entirely new kind of physical measurement that we haven't even invented yet? Take a stance and let me know. And if you want to keep going, if you are not ready to close the case file just yet, click the video that is hovering right there on your end screen. Because our next audit picks up exactly where this current mystery stops feeling comfortable, and we dive straight into the anomalies. Subscribe to the channel if you want to learn exactly how to read the universe's most heavily guarded receipts with me, analyzing one impossible test at a time, without ever blindly worshipping any one idea.